A recurrent neural network, RNN, is a type of artificial neural network that's designed to recognize patterns in sequences of data, such as text, genomes, handwriting, or the spoken word. It's called recurrent because it performs the same task for every element in a sequence, with the output being dependent on the previous computations. Think of it like this: imagine you're watching a movie, and you pause it halfway through. Even without the movie playing, you still remember what happened in the first half. This memory helps you understand what's happening when you press play again. RNNs work in a similar way when processing sequential data. They remember some information about what has been calculated so far. In more technical terms, RNNs have loops in them, allowing information to be passed from one step in the network to the next. These loops give recurrent neural networks a kind of memory. They can process not just the current input, but also what they have perceived previously in time. This makes RNNs very effective for tasks where the order of the data matters, such as language modeling, where words in a sentence often depend on previous words, and time series analysis, where the value at a certain time may be a function of past values. However, traditional RNNs can struggle with long sequences due to issues known as vanishing and exploding gradients, which can be mitigated by variants of RNNs like long short-term memory, LSTM, and gated recurrent unit, GRU. In a recurrent neural network, RNN, we have something called an activation at each step in time. This is denoted using letter A. The activation is a kind of internal memory of the network at a particular moment. It's calculated based on the information from the previous step's activation and the current input data. This calculation involves a set of weight parameters specific to the activation and a bias term, which are used to scale and shift the combined information. An activation function is then applied to this result, which can help introduce nonlinearity and enable the network to learn more complex patterns. The output at each time step is then calculated based on the current activation. This also involves a set of weight parameters, this time specific to the output, and another bias term. These are used to scale and shift the activation, and then another activation function is applied to generate the final output. One of the key features of RNNs is that the weight parameters and bias terms used in these calculations are shared across all time steps. This means that the same weights and biases are used for each input, regardless of its position in the sequence. This is what allows RNNs to process input sequences of varying lengths and to generalize across them. Gated recurrent units, GRUs, and long short-term memory, LSTM, units are two types of layers used in neural networks to help solve problems with standard recurrent neural networks, RNNs. They're both designed to help the network remember information for longer periods of time, which is particularly useful when dealing with long sequences of data. Let's start with GRUs. Think of a GRU as an advanced version of an RNN that has a better memory. It has a system of gates, which are like checkpoints or filters that manage the flow of information. These gates decide what information should be kept or discarded at each step in the sequence. This allows a GRU to remember important information for longer periods of time and forget less important information, making it more effective at processing long sequences of data. Now, let's talk about LSTMs. An LSTM is like a supercharged GRU. It has not one, not two, but three gates, each with a specific job. One gate decides what information to forget, another decides what new information to add, and the third decides what information to output. This intricate system of gates allows an LSTM to keep track of information over even longer periods of time than a GRU. It's particularly good at understanding things like long sentences or long time series, where the meaning depends on understanding the whole sequence. In summary, both GRUs and LSTMs are advanced types of RNNs that are better at processing long sequences of data. They do this by using systems of gates to carefully manage the flow of information, deciding what to remember and what to forget. This makes them very effective for tasks like language modeling, speech recognition, and time series prediction. In summary, Both GRUs and LSTMs are advanced types of RNNs that are better at processing long sequences of data. They do this by using systems of gates to carefully manage the flow of information, deciding what to remember and what to forget. This makes them very effective for tasks like language modeling, speech recognition, and time series prediction. In this code, we're using TensorFlow, a powerful tool for machine learning, to create a model that's designed to handle sequential data, like a series of measurements taken over time. This model is a type of artificial neural network known as a long short-term memory (LSTM) network. The model is made up of a sequence of layers, each performing a specific task. The data will pass through these layers in order, with each layer transforming the data in some way. The first layer is an LSTM layer. This layer is like a supercharged detective, capable of recognizing patterns in the data and remembering them for a long time. It's designed to handle sequences of data, where the order of the data points matters. The number 32 in the LSTM layer means that it has 32 memory cells, each capable of learning and remembering a specific pattern in the data. The return_sequences equals true argument means that this layer will output a sequence of data that has the same length as the input sequence. This is useful when you want to stack multiple LSTM layers or when you want the output to be a sequence of the same length as the input. The second layer is a dense layer. This layer is fully connected, which means each neuron in this layer is connected to all neurons in the previous layer. The units equals number_features argument means that this layer will have as many neurons as there are features in the data. This is typically the final layer in the model, and its job is to take the high-level representations learned by the previous layers and turn them into a final prediction. In essence, this code is creating a neural network with an LSTM layer and a dense layer. This network would be capable of learning complex patterns in sequential data, making it useful for tasks like time series analysis or natural language processing.